Welcome to part 2 on foundations of combinational circuits. Let's review the important parts from the first part. In the first part, we showed that we can describe circuits using netlists, and we also showed how to represent a netlist in which all the nets are simple using a directed graph. So to every netlist H, we attach a directed graph H. In a nutshell, what we do is we take a simple net and we represent this net as a collection of directed edges that emanate from the vertex whose output feeds the net. Using this graph representation of netlists, we define what a combinational circuit is. A combinational circuit is a netlist in which every net is simple and the corresponding directed graph is acyclic. So that's the definition of a combinational circuit. Now, given this definition of combinational circuits, we want to focus on 4 important properties of combinational circuits: completeness, soundness, simulation, and delay analysis. Completeness means that for every Boolean function, there exists a combinational circuit that implements the function. Soundness means that every combinational circuit implements a Boolean function. Simulation means that given a combinational circuit, if you tell me what the values of the inputs are, I can compute the values of the output. Delay analysis means that I can tell you how long it takes until the outputs are consistent with the values of the inputs, namely when the values of the outputs are a Boolean function of the values of the inputs. Our plan: we will present an algorithm for simulation and delay analysis. We will present an algorithm. This algorithm that we present implies soundness. And finally, we will prove completeness by implementing Boolean formulas as by combinational circuits. To simplify the exposition of simulation, we will make a few assumptions. First assumption is that for every gate, it has a single output terminal, unless it's, of course, an output gate. We have at most 2 input terminals per gate. The fan-in is bounded by 2. And that the gates we have, in case they have an in degree of 2, implement a commutative Boolean function. And these assumptions help us simplify the port information of wires. So for example, if I look at this AND gate which feeds the OR, and this inverter that also feeds the OR, I can give the inverter the name V1, the AND the name V2, the OR the name V3, and just talk about the wire from V1 to V3 and the wire from V2 to V3. And I don't care exactly which input port of V3 is fed by these 2 wires, because the OR gate is a commutative function. Now, we will use the following convention. If we look at the vertex V, it has a single output terminal, unless it's, of course, an output gate. And then we will refer to the output of the vertex V as V of t. And when we're talking about an output gate, we will refer to the input, the single input of V, as V of t. We will assume that our circuits have k inputs, and we denote them by x1 up to xk. And we will use x with the vector symbol above it to denote the k inputs of the circuit. So we have a circuit C with k inputs, x1 up to xk. Our goal is to prove the simulation theorem, which says the following. If I have a circuit C with k inputs, and these inputs are stable during the interval t1 to t2, then for every vertex v in the directed graph that corresponds to the netlist of the circuit, I can attach a Boolean function f of v and a propagation delay tpd of v. The Boolean function f of v tells us if I know the k bits of the input, what is the output of this vertex? And the tpd of the vertex v tells me when does this output become valid. It will become valid after a delay of tpd of v. It is important to make a distinction between the propagation delay of a vertex v in a circuit and the propagation delay of the gate which appears in that vertex. So consider, for example, a combinational circuit with inputs, and I'm looking now at a specific gate in this circuit which is modeled by this vertex called v. So I have a specific gate here, G, for example, an AND gate, and I want to make a distinction between the propagation delay of the AND gate and the propagation delay of the vertex V. Okay? The propagation delay of the AND gate is simply the time that elapses from the minute that the inputs of the gate are stable until the time in which the output reflects the values of the inputs. The propagation delay of V tells us how much time elapses from the minute that the inputs of the circuit are valid or stable until the output of V reflects the values of the inputs. So TPD of G is a local thing, and TPD of V is a global thing because it deals with the global inputs of the circuit and how they influence the output and the time it takes them to influence the output of the gate. The proof will be by an algorithm, the proof of the simulation theorem. This will be a simulation algorithm. It's very similar to the evaluation algorithm of Boolean formulas. It sorts the vertices in topological order, and given the values of the inputs, it evaluates the value of every output terminal. And it also computes the accumulated delay along paths in the combinational circuit. So this is the description of the simulation algorithm. The input C is a description of a combinational circuit. G is our directed graph. Pi is the assignment of gates to the vertices in the graph. And the second parameter X is the K input bits. We begin by sorting the vertices of the directed graph G in topological order, and we denote this ordering by V1, V2 up to Vn. The second stage, we scan the vertices from V1 until Vn. And for each Vi, we compute the value of the function fVi and the propagation delay TPD of Vi. In this scanning of the vertices, we need to consider three cases. Either the in degree is 0, or the in degree is 1, or the in degree is 2, because we assume that the fan-in is bounded by 2. If the in degree is 0, then Vi is simply an input gate. It feeds xj, and we know that the value of the output of this vertex is always xj, and this will happen immediately. So we assign fVi of x to be equal to xj, and the propagation delay of Vi to be 0. In the second case, where the in degree is 1, there are two options. Either Vi is an output gate, it has a single input, or Vi is an inverter, has a single input and one output. If Vi is an inverter, then this inverter is fed by another vertex, say Vj, and we know that j is less than I because of the topological ordering. So it means that we already scanned Vj, and we already determined the value of fVj. And what will be the value of the output of the inverter? It will be the negation of fVj of x. So we set fVi of x to be the negation of fVj of x. When will this output be valid? Well, we take the time in which this fellow becomes valid, this is TPD of Vj, and we add to it the local delay of the inverter, and therefore Vi will become valid at time t1 plus TPD of Vi. The second case, in which Vi is an output gate, is handled very easily because Vi is fed by some Vj, and we know that Vi is just the value of this wire, will simply equal the value that is output by Vj, and therefore Fvi of x equals Fvj of x, and the propagation delay is the same as the propagation delay of Vj, because no extra delay is incurred by feeding an output gate. The third case is when Vi has an integrity of 2. Let's assume that the gate residing in Vi is an AND gate, and then we have two vertices which are feeding the inputs of the AND gate. We denote them by Vj and Vk. Because of the topological ordering, we know that j is less than I and k is less than I. So therefore we have already scanned Vj and Vk. We know the functionality that is output by Vj. We know the functionality that is output by Vk. And now all we need to do is perform the AND of these two bits, and this would be the definition of Fvi of x. Recall, b of pi Vi is simply the Boolean function of the gate residing in node Vi. In our case, it's an AND. What about the propagation delay? Well, we know when this signal becomes valid. We know when this signal becomes valid. We take the last one, so we take the maximum between the two propagation delays of Vj and Vk. At that time, we're sure that both inputs will become stable, and to that we add the local delay of the AND gate, and this will be the accumulated delay until the output of Vi. We want to prove the correctness of the algorithm, of the simulation algorithm. What does that mean? We want to claim the following. We want to claim that for every I from 1 to n, these are the indices of the vertices after we sort them in topological ordering, and for every value of the inputs, and for every time t in the interval t1 plus the TPD of Vi, this is the I that appears over here, until time t2, the value of the output of Vi equals Fvi of x. This will be the correctness of the simulation algorithm. The proof of this theorem is by complete induction on I, the index of the vertex in the topological ordering. Okay, so to make the proof simple, let's assume that the inputs appear first in the topological sorting, namely V1 outputs x1, V2 outputs x2, and so on up to k. And now we apply complete induction on n. The basis for the inputs is very easy because xi, which is implemented by vertex Vi, simply outputs xi. So the propagation delay is 0, and the function is correct because this is exactly what the algorithm does. The induction hypothesis says that for every j less than I, we have the right functionality during the right time interval. And now we want to prove the induction step. The induction step has to deal separately with three cases. Either the node Vi is an inverter, or the node Vi has a fan-in of 2, let's say it's an AND gate, or an OR gate, or whatnot, or Vi is a output gate. Now, the case of an output gate is easy. I'm skipping it, and I'm leaving the case of an inverter as an exercise, and I'll focus on the case that Vi is the gate residing in Vi has a in degree of 2, and in particular, let's assume that it is an AND gate. Okay, so this AND gate is fed by two vertices, Vj and Vk. Topological sorting tells us that j is less than I and k is less than I, therefore Vj and Vk have been already scanned. The induction hypothesis tells us what is the value of Vj and Vk at time t, where t goes from t1 plus TPD of Vj until t2, and we have this interval for Vk. It tells us this signal is going to equal the function that we assign to Vj, and this signal will equal the function that we assign to Vk. Now, what does Vi do? It takes these two inputs and it does the AND of them. So we have Vi of t equals the AND of Vj of t and Vk of t for every t in the interval starting from t1 plus tpt of vi until t2. What is tpt of vi? Well, tpt of vi, we look at the last input, which becomes stable. That would be the maximum of the two propagation delays, plus the local propagation delay of the end. Okay? Now, Vj of t equals f of Vj of x by the induction hypothesis. Vk of t equals f of Vk of x by the induction hypothesis, because we're referring here to an interval which is contained both here and here. So we can do this substitution, and this is exactly what the algorithm assigns as the function of Vi of t, and therefore Vi of t indeed equals what we wanted. You may ask, what happens if I run the simulation algorithm and I have some freedom in the first line where I compute the topological sorting? Maybe my directed graph has more than one topological sorting. So let u1 up to un denote one topological sorting of the vertices, and v1 up to vn denote another topological sorting. Now the question is the simulation algorithm influenced by the choice of the topological sorting? That will it output different things if you use the first topological sorting or if you use the second topological sorting? And of course, you wouldn't want it to be influenced by the choice of the sorting, and we need to prove it. Okay, so these are the two topological sortings. I execute the simulation with respect to the first one, I execute the simulation with respect to the second one, and I want to have the same outcome. So suppose that ui is a vertex that appears here, is some vj in this list. And we want to prove that the both executions of the simulation algorithm will assign the same functions to these vertices and the same propagation delays. How would we prove that? By complete induction on I. The induction basis, well, U1 has to be an input gate, and if it's an input gate, then one can easily show that in fact these functions have to be equal and the propagation delays are 0. The induction hypothesis will say, well, you get these equalities for every j less than I. Namely, if I look at uj, where j is less than I, and I look at its counterpart, vk, which appears here in the second list, then the algorithm assigns the same functionality and propagation delays to vk and to uj. In the induction step, we consider ui. Ui is either an input gate, an inverter, an output gate, or a gate with two inputs. These two cases are very easy. I'll skip them. This I'll leave as an exercise, and let's focus on the case that ui has a AND gate placed in this node. Good. So we have the node ui fed by uj and uk, and in the second topological ordering, ui appears as vt, uj appears as vr, uk appears as vs. Now, j and k are less than I because of the topological sorting, and now the induction hypothesis tells us, because j and k are less than I, that the functions attached to VR and uj are the same, the functions that are attached to vs and uk are the same, and they have the same propagation delays. Now we look at what vt outputs. The function which is attached to vt is the AND of the functions which are attached to VR and vs. But f of VR equals f of uj, f of vs equals f of uk. And this is exactly the function which is attached to ui. So we get that these two functions are equal as required. What about the propagation delay? The propagation delay of vt is set to the maximum between the propagation delays of the two vertices that feed it, plus the local propagation delay of the AND. Now, by the induction hypothesis, this equals this, and this equals this, and this is exactly the propagation delay which is computed by the simulation algorithm for ui. So this completes the proof. Okay, now we want to focus on soundness. What does soundness tell us? Soundness tells us that every combinational circuit implements a Boolean function. In fact, the simulation theorem attaches a Boolean function to every output, in particular to the output gates, And therefore we can view a combinational circuit as a macro gate, which implements a Boolean function with k inputs and, let's say, L outputs, where L denotes the number of output gates of the circuit. Notice that all instances of the same combinational circuit implement the same Boolean function and have the same propagation delay, just as if you were to use many AND gates in your circuit. I want to emphasize that the simulation algorithm is a generalization of the evaluation algorithm of formulas or parse trees to directed acyclic graphs. In fact, the computation of the propagation delays by the simulation algorithm is a computation of longest paths in directed acyclic graphs, in which you have non-unit delays on the vertices. So delta V denotes the delay which is given to a vertex V. Okay, each gate has some delay which is associated with it. And the algorithm for finding longest path lengths in a directed acyclic graph with non-unit vertex weight proceeds as follows. It sorts the vertices in topological ordering, and then it scans the vertices from the first to the last, and you do the following. If Vj is a source, then the longest path that ends in Vj has a delay of delta of Vj. In our case, delta of Vj, because it's an input gate, had a value of 0. Otherwise, you look at Vj, and you look at the last input that feeds Vj, so you take the maximum over all the i's that have an directed edge entering Vj, you take the maximum of their delay, and you add to it the local delay of Vj, and that gives you d of Vj. Sometimes your circuit, in addition to the k inputs x1 up to xk, may want to have inputs which are constant 0 and 1. For that you would have to need 2 more input gates labeled in 0 and in 1, and you could modify the simulation algorithm so that it would also be able to handle the case that the inputs, some of the inputs are constants, 0 and 1. Completeness. Completeness means that we want to show that for every Boolean function there exists a combinational circuit that implements the Boolean function. Now, how do we do that? We know that and, or, and not constitutes a complete set of logical connectives. So, given a Boolean function b, we can represent it by a Boolean formula phi over these connectives. Now what we need to do is to show how we can implement a Boolean formula by a combinational circuit. I will prove this by an example. Consider the following parse tree. In this parse tree, you see that x1 appears twice as a leaf. So what you do is you coalesce together all the instances of x1, and you make them into one node called in of x1. And you connect this in of x1 to whoever was fed by x1. And you do the same thing with x2. You replace x2 with an input gate called in of x2, and you connect it to whatever you need to connect it to. And now you take the root and you connect it to an output gate, which is called out of y. Great. So now we have a combinational circuit which implements the same thing that this formula implements. And this formula was meant to implement some Boolean function we're interested in. So in general, what do? We take the parse tree of a Boolean formula, we merge all the leaves that are labeled by the same variable, we have a DAG as a result of this merging, no cycles are introduced, we label the sources by input gates, we add the root, this is the output gate, we add this root, which is fed by the original root of the parse tree, and label it by an output gate, and we get our combinational circuit, which implements a Boolean formula. One thing that we might want to do is to attach a cost to every combinational circuit. Okay, so this circuit uses gates and inputs and output gates, and we attach a cost to every such gate. Okay, usually input and output gates will have a 0 cost. Now the cost of a circuit is simply the sum of all the costs of the gates that appear in the circuit. Recall that pi of V is the gate that resides in node V. We can also attach a propagation delay to every vertex by the simulation algorithm. The propagation delay of the whole circuit is then defined to be the maximum over all the vertices of the propagation delay of V. Okay, we often refer to the propagation delay of a combinational circuit by its depth or as its depth or its delay. Now we can also attach propagation delays to paths. The propagation delay of a path in G is defined as the sum of the propagation delays of the gates along the path. Okay. The following claim says that if you take the maximum delay of a vertex in a circuit, it equals the maximum delay of a path in the circuit. Okay? This is a very interesting claim because the simulation algorithm did not enumerate all the paths and take the longest path. It computed the longest path indirectly. Okay? So this is an important claim, and I'll leave it as an exercise to prove this claim. We say that a path P in G is critical if the delay of the path P equals the delay of the whole circuit. And we focus on critical paths that are maximal, namely cannot be further augmented by vertices. This means that a maximal critical path begins in an input gate and ends in an output gate. Now, I want to emphasize that there might be more than one critical path in a combinational circuit. As usual, we have the distinction between semantics and syntax. Semantics, in the case of combinational circuits, is simply the function that the circuit implements. It's a Boolean function. A circuit that is not combinational may have an output that depends on the history. So semantics of such non-combinational circuits cannot be described by a Boolean function. But in the case of a combinational circuit, the semantics are very simple. It's just a Boolean function. Syntax. Recall that syntax is just a formal set of rules that govern how grammatically correct circuits are constructed from smaller circuits. Now, when we talk about syntax, we don't really care about the functionality of each gate, whether it's an AND gate, an OR gate, a XOR gate. If it has, all we care about is the fan-in of the gate. And another thing we care about are the rules for how we connect gates together. For example, we use simple nets. All the terminals have to be connected to a net, and so on. Now, following the syntax does not guarantee that the resulting circuit is useful. However, if you follow the syntax, then you know for sure that the functionality is well defined, that you could easily simulate the combinational circuit, and you can easily perform timing analysis. So, in this chapter, we defined design rules for building combinational circuits. And these design rules define the syntactically correct circuits. And the interesting part in the simulation theorem is that if you follow the design rules, then you get combinational circuits, and these combinational circuits implement Boolean functions, can be easily simulated, and you can easily analyze their timing. Now we're left with the following task. Given a Boolean function B, design a combinational circuit C that implements B with the lowest delay and lowest cost possible. To summarize, we defined what combinational circuits are. We used a bottom-up approach. We started with the basic building blocks of gates and wires, where each gate has a simple specification of a function and a propagation delay. We applied a syntactic definition for how to build combinational circuit, and this syntactic definition only depends on how you connect together terminals. This is referred to as topology of the circuit. And you can check very quickly whether a given circuit is indeed a combinational circuit. You can also simulate the circuit in linear time. And you can say what is going to be the digital value of every wire in the circuit. Moreover, you're going to be able to say how long it takes until this computation is completed. The computation done by the circuit, not the simulation. We attach two quality measures to every combinational circuit, cost and propagation delay. The cost of a combinational circuit is the sum of the cost of the gates in the circuit, and the propagation delay of a combinational circuit is the maximum delay of a path in the circuit. Thank you very much.